Okay, so let's look at part B of that one. We've already done part A, but I'm going to show my work up here because it's a nice clear space and I can do that and have it make sense. So what I know is I know that I have the loops that we looked at before, and I know that they have dimensions. So the length is 0.2 meters. The width is 0.06 meters. The resistance is 0.02 meters. And the speed at which they are being moved is 0.3. Okay, so loop A. We said that there was no current induced in loop A, so if there's no induced current, I don't need to worry about A. All right. Now if we look at loop B, here's my field into the plane of the page. Here's my loop. My loop is a red loop like that. And I just made it red because I like that color. There's my pull. Somebody's exerting a force on it. And as it gets pulled to the right, there's less and less of the loop in the magnetic field. So I can say that the flux of the magnetic field is decreasing. So EMF is going to be equal to BLV sine theta. Well, theta is the angle between the velocity in the field, and it's a right angle. So I can say that's the sine of 90. Which is 1. So that's going to give me the maximum EMF. So the EMF is going to be B. What do I know about B? I didn't write it down. It's a given. B is 0.40 Tesla. So I have 0.40 Tesla. Then I have the length, and I'm going to come back to that in a minute. And then I have the speed. So if I want to look at this length, this is the 0.20. And this is the 6 centimeters, or the 0.06 meters. You want the dimension that is cutting through the field. You want the dimension that's being pulled by this force. So you only want that value right there. Okay? 0.06 meters. Now, up here they tell you that in B, C, and D each have 0.09 of their meters of their length, not in the magnetic field at the time shown. Well, that's okay. I don't really care, though. The only thing that I'm worried about is how is this 6 centimeters cutting across that field. Well, it's pulling at that speed, and it's going through that much field. So if I multiply 0.4 times 0.3, I get 0.12, and then I multiply that by 6/100ths, I get 0.0072 volts, but I'm going to pause and make sure that's right. All right, so there's my EMF. Now what I need to find is the current, because that's what Part B asked me to find. It asked me for the magnitude of the induced current. So I is equal to V over R. My EMF is my voltage, 0.0072 volts. My resistance is 0.002. Oh, I'm sorry, I put one too many zeros in there. 0.02 ohms. So if I take 0.2 and divide it by 0.02, that's 7.2 times 10 to the minus 3 divided by 2 times 10 to the minus 2 gives me 0.36. But I'm going to check that because I'm probably going to be off by a 0. I'll be back. But that looks like a great answer when I checked it on the calculator, so I think we're good there. Now, if you look at C, it says, B says, what is the magnitude of the induced current loop generated in the loop A and B? Well, we only had to do A and B. That's loop B. We said loop A would be 0. If you wanted to do loop C, let's go back and take a look at loop C. So we're going to backtrack a little bit. Loop C has the exact same dimensions. It's being pulled along that exact same side, so it's going to induce the same amount of current. D has no current induced at all. So I'm going to go ahead and make a note of that. So the current for C would also be 0.36 amps. And the current for loop D would be 0 amps because there is none. Because the flux does not change. All right, so that's good on those two. Let's move on down to Part C of the question. Part C says, what is the magnitude and direction of the induced magnetic force experienced by the loop C at the instant shown? All right, so here's my loop C. X's are everywhere because the field is into the page. And I'm taking a different color for loop C. And it's being pulled in that direction if I remember what I'm doing. So let me double check and make sure, yep, that's good. So they want to find the force. Well, F is equal to BIL sine theta. Theta is the direction, is the angle between the field and the motion. Okay, so it's a right angle, so that's a sine of 90. So my B was given to me as 0.40 Tesla. My current we figured out was 0.36 amps. And again, the force is being applied to the 6 centimeters or the 0.06 meters. So if I multiply that time, those two together, you get 0.144, and then 6 100ths of 0.144 is 0.00864, I think. So I'm going to check that real quick. All right, so we're good there. Now we need the direction. Well, it's being moved in that direction, and being moved in that direction is going to cause an EMF to be induced, and as a result, a current to be induced. So I want to talk about that first. So I'm going to say, well, it is increasing into the page, so I need to set up a current that will increase out of the page. So I'm going to point my thumb of my right hand out of the page, and my fingers are going to curl counterclockwise. So there's the direction of the current flow. So then I'm going to use my right hand, and I'm going to say, well, the field is into the page. That's my fingers. The current is flowing to the left, so there's got to be a force of the magnetic field, and you can't see that very well. So there's got to be a magnetic field, a force from the magnetic field acting in that direction. Okay? And honestly, you don't even have to go through all that. You know that for every action, there has to be an equal and opposite reaction. Okay? So I'm going to move on. Let's get rid of that. You can pause it if you still want to look at it. Now I want to look at this one here. We didn't talk about induced EMF, or motional EMF, I should say, but I'm fixing to talk about it with you now. Very, very straightforward. All right, so I want to find the EMF. Well, I know a formula that I want you to use, but I want to show you where it came from. So EMF is equal to change in flux over change in time. Change in flux is B, because the field is constant. Delta A, change in area, because you're moving it to the right, the area is going to change. It's going to increase over delta T. Well, area is length times width over delta T. Well, the length is this distance here. It's not changing. What's changing is the width of the rectangle. So it's going to be B, L, delta W over delta T. Well, delta W over delta T is also the same thing as the speed, the velocity. So I'm going to say that it's equal to B, L, B. And that's, again, sine theta. But theta is 90, so it's all good. So now I need to go back and look at my given. So my field is 1.20 Tesla. My length, right there, 0.80 meters. My velocity is given to me as 2.5 meters per second. I know the mass of the rod, not going to matter, but they gave it to me just in case they could trick me. And I know the resistance of the entire circuit once that rod makes contact with those two wires is 24 ohms. All right, so if the EMF is equal to BLV, then I'm going to plug in 1.2 Tesla. My length, again, is 0.80 meters, because that's the dimensions that's cutting across the field. My velocity is 2.5. So if I do the math, I know that this is 2, and 2 times that is 2.4 volts. But that's not, yeah, that's what they want, 2.4 volts. All right, so we're good there. Now there's a part B, of course, so let's go to that one. If I can figure out how to operate this technology. All right, then it wants to know the magnitude of the induced current. So the induced EMF is V, and V is equal to IR. So 2.4 volts over resistance of 24 ohms is I. So I is 1/10 of an amp. Now I know they're going to ask me about the direction of the current flow, so I'm going to go ahead and figure that out while I have this picture up here. So if you think about it, if you're pulling it this way with an applied force, then the area is increasing, so the flux is increasing. because remember flux is BA cosine theta, and theta in this case is 0 degrees. So as long as area increases, this has to go up. So if that's going up, it's increasing out of the page. I need to cause a field to be generated that increases into the page. So if I put my thumb into the page and curl my hands, my current looks like to me it's going to flow clockwise. Okay? All right, let's move on. I think that was part C, but we kind of jumped ship. Yes, is it going to be induced? Yes, it's going to be clockwise or counterclockwise. So here's how I would explain it. And this is not an explanation where you can just put down a couple of words and be good to go. You need to be able to show that you understand what you're talking about. So I would say as the rod slides to the right, the flux is increasing. Okay. I need to create a current that generates a magnetic field that is increasing into the page. Okay, using the right-hand rule, I see that the current must flow clockwise. Okay, then it says down here, determine the magnitude and direction of the force. Well, F is equal to BIL sine theta. B was given to me as 1.20 Tesla. The current we figured out was 1/10 of an amp. And the length was 0.8 meters. And theta is sine of 90. So if I do my math correctly, 1/10 of 1.2 is 0.12. 0.12 times 0.8 is, I believe, 0.96 newtons. But I'm going to check that real quick. So let's say 0.1 times 1.2 times 0.8. I needed another 0, I can already tell. Should have been 0.096. Good job, Miss Walker. 0.096 newtons. Now, that's the magnitude. I want the direction. So if the loop is being pulled to the right, then I need a force that acts to oppose that motion, because that's what Newton's law tells me that I need. And there's my force. All right. So that is what we did while you were gone. They had some homework. I'm going to post the homework and a copy of these notes on my web page, so you can go and pick them up and print them out. If you don't do that, then come by my classroom and get a copy, but you need to come to class on Thursday with everything taken care of. Thanks a lot.